Welcome back, future grid engineers, to today's explainer. Look, we're skipping the 101 stuff today and diving straight into the deep end of the Power Grid Cyber Twin. We're going to look specifically at how these digital twins use some pretty heavy mathematical models to predict, simulate, and, ultimately prevent physical grid meltdowns. So let's just get right into it.
All right, here's the game plan for today. 1. Enter the Cyber Twin. 2. Simulating physical heat patterns. 3. The IoT sensor network. 4. The 5G gateway and security. And 5. Visualization and alarms. Basically, we're building this whole thermal state monitoring system from the ground up using the industry-standard ISA 95 architecture. We'll start right at the source, the actual physical heat generation, and track that data packet all the way to the operator's screen.
Section 1. Enter the Cyber Twin.
So what are we actually dealing with here? Well, let me be clear. This isn't just some video game. This is a meticulously crafted digital twin. It's heavily inspired by real-world, bleeding-edge deployments, specifically Schneider Electric's wireless sensors. And it's built for one reason: your engineering education. It lets you get your hands dirty and practice without, accidentally frying a multi-million-dollar physical asset.
Looking at this level 0 to level 2 architecture, it's like a giant map bridging two worlds. You've got your simulated physical components down at the bottom, local IoT controllers hanging out in the middle, and your centralized control centers sitting up top. Literally everything we are talking about today maps right onto this structure.
Moving on to Section 2, simulating physical heat patterns. This is where things get really interesting.
Across your simulated grid, you have 17 virtual sensors strategically deployed. They're keeping tabs on everything, from your massive step-up transformers right down to your battery energy storage systems. And here's the kicker. The simulator is generating a brand new, highly accurate temperature reading for every single one of those sensors, every single second.
Now, you might be wondering, how do we actually fake that physical heat so convincingly? Well, the algorithmic formula doing the heavy lifting here is it's elegant. First, it grabs a baseline, the real-time ambient weather. Then, it throws in a tiny random environmental fluctuation, maybe 0 to 1 degree Celsius, just to give it that messy, real-world feel. But Step 3 is the absolute crucial part for us grid engineers. It calculates and adds the heat generated by the electrical load losses of that specific component. Meaning, if you push more current through a virtual transmission cable, the mathematical load loss shoots up and bam, the simulated temperature spikes right along with it.
This math directly dictates the operational states of your assets. As the current ramps up through your transformers, so does the heat. There are 3 distinct operational temperature ranges you absolutely need to commit to memory. An idle component is just going to chill near ambient temperature, around 15 to 35 degrees. But your continuous normal operating state, that pushes things up into the 70 to 90 degrees Celsius neighborhood. Now, when extreme weather hits or demand skyrockets and you hit an overload condition, suddenly you're staring down 105 to 130 degrees.
But listen, here is the number that should literally keep you up at night: 160 to 250 degrees Celsius. If you ever see a transformer or a cable connector hit this critical short circuit limit, you are way past dealing with simple inefficiencies. You are looking at severe equipment degradation, melting insulation, and a guaranteed imminent fire risk.
So we've essentially conjured this perfect thermal data out of pure math, down at level 0. But how do we securely transmit it across a simulated substation? Because let's be real, generating the temperature is only half the battle. As an engineer, your job is to make sure this highly sensitive data survives the treacherous journey up the network stack without getting intercepted, or worse, spoofed.
Which brings us to Section 3, the IoT sensor network.
Let's move up the stack and actually track the journey of our little simulated data packet. The physical world simulator, where all that math we just talked about happens, takes that raw thermal data and tosses it via a UDP connection right into our simulated ZBRT1 IoT sensor. Using UDP here is smart because it completely isolates the physical simulation from the network communication layer.
Okay, so what does the virtual sensor do with that raw number? It definitely doesn't just hand it off. First, it stamps it with a precise timestamp. Then, it takes that temperature and the timestamp and wraps the whole thing in some heavy-duty AES-128 encryption using a specific key and an initialization vector. Finally, it packages that payload into the MQTT protocol and blasts it out across a simulated 2.4 GHz Wi-Fi network.
Section 4, the 5G gateway and security.
Next up, our encrypted data packet slams into the 5G IoT gateway. Think of this gateway as the ultimate bridge between the local substation and the remote control center. It's an absolute workhorse. It actually juggles two separate databases to get the job done. Database 1 is your keyring. It manages all the cryptographic keys for the incoming sensors. Meanwhile, Database 2 acts as a local historian, archiving the thermal history of your assets. Just in case a storm knocks out your connection to the main control room.
To build this into a secure, unified data stream, the gateway runs a super slick 5-step process. First, it catches the MQTT payload. Second, it decrypts that incoming sensor packet using the keys it pulled from Database 1. Third, it aggregates that reading with the data streaming in from the other 16 sensors. Fourth, it archives the whole batch locally in Database 2. And fifth, and this is absolutely crucial, it re-encrypts the entire aggregated package with a brand new gateway-specific AES-128 key.
This whole setup, this is what we call a two-layer security architecture. On the outside, you have transport-level security, like SSL or TLS, securing the actual Wi-Fi and 5G pipes. But inside those pipes, the data payload itself is basically locked in a vault using application-level AES-128 encryption. This double-layer approach is exactly the kind of architecture you are going to implement out in the real world. It's how you stop malicious actors from spoofing temperature data to cause fake blackouts, or even worse, masking a real thermal runaway event.
All right, final stretch, Section 5, Visualization and Alarms.
Let's step into the Level 2 control room and see what the operator is actually staring at when things start getting a little too hot. All that simulated math, the UDP transfers, the AES encryption, the MQTT routing, it all culminates right here. This is a Flask-based web human-machine interface. It's where raw data transforms into actionable engineering intelligence. And the beauty is, you can deploy this locally on a ToughPad right inside the substation. Because let's be honest, in the middle of a crisis, you don't have time to stare at spreadsheets of raw numbers. Your automated alarm system is constantly checking the telemetry against predefined thresholds, using a strict color coding system so you can instantly spot trouble. Yellow? You're nominal. Orange? That's a warning. Pay attention. Red means you've officially crossed safety thresholds. But if you see blinking red, you've got a critical overtemperature condition on your hands, like a catastrophic cable overload or a battery thermal failure, and you need to pull the plug immediately. Of course, you can't be in the substation 24/7. For remote operations, that 5G network pushes all this aggregated, re-encrypted data straight into the Centralized Operator Control Center HMI. This gives you a literal God's eye view of the entire grid's thermal health on one massive screen. You can spot a heat spike in a step-up transformer and immediately correlate it with a load surge way out on the distribution side. Which brings us to a really critical question I want to leave you with today. If a cyber twin can perfectly simulate a catastrophic thermal disaster just by crunching ambient weather data and electrical load losses, what is stopping you from using this exact algorithm to predict the precise minute a real-world grid is going to fail? Think about that. As you take these concepts out of the simulator and into the field, remember, mastering the digital twin is just step 1. Step 2 is mastering the future of our global energy infrastructure. Thanks for hanging out with me with this explainer, guys. Keep building and stay curious.